To explain this behavior, Werner postulated his theory as follows. 1. Most of the elements exhibit two types of valence, namely primary valence and secondary valence, and each element tend to satisfy both the valences. In modern terminology, the primary valence is referred as the oxidation state of the metal atom and the secondary valence as the coordination number. For example, according to Werner, the primary and secondary valences of cobalt are 3 and 6 respectively. 2. The primary valence of a metal ion is positive in most of the cases and 0 in certain cases. They are always satisfied by negative ions. For example, in the complex cobalt-3 chloride, 0.6 NH3, the primary valence of Co is +3 and is satisfied by 3 Cl ions. 3. The secondary valence is satisfied by negative ions, neutral molecules, positive ions, or the combination of these. For example, in cobalt-3 chloride, 0.6 NH3, the secondary valence of cobalt is 6, and is satisfied by 6 neutral ammonia molecules, whereas in cobalt-3 chloride, 0.5 NH3, the secondary valence of cobalt is satisfied by 5 neutral ammonia molecules and a Cl ion. 4. According to Werner, there are two spheres of attraction around a metal atom ion in a complex. The inner sphere is known as coordination sphere, and the groups present in this sphere are firmly attached to the metal. The outer sphere is called ionization sphere. The groups present in this sphere are loosely bound to the central metal ion and hence can be separated into ions upon dissolving the complex in a suitable solvent. The primary valences are non-directional while the secondary valences are directional. The geometry of the complex is determined by the spatial arrangement of the groups which satisfy the secondary valence. For example, if a metal ion has a secondary valence of 6, it has an octahedral geometry. If the secondary valence is 4, it has either tetrahedral or square planar geometry.